Thank you. So I'm going to present you today about a part of the internal persistence layer of our MyStekz platform. So for those who don't know me, my name is Dulaj Disanayaka. As I said, I'm a senior engineer at Stekz, and I'm the main developer behind the StekzVFS. So before we go any further, I want to... can hear me, right? Yeah. Before we go any further, I want to make this small disclaimer. Just consider this talk as a war story of how we went about and solved a very specific problem we had. And don't consider this as a definitive guide on how to approach these kind of problems. We are still experimenting and improving StekzVFS, so there might be some questionable design decisions here for you. So if you don't know me, if you don't know, MyStekz is a biz DevOps platform which allows you to design, develop, and maintain your IT solution in a domain-driven design architecture. In the biz stage, this allows you to modularize your application into domains and the process they expose. These processes are defined using business process modeling notation or BPM and files, as you see here. To persist this data in a structured way, we had few requirements to fulfill. First of all, we needed to store our domains, products, and process as subgroups of one another. Process definitions, we needed to be stored as BPMN files inside the process subgroup. We also wanted to let users upload any files they want into any of these subgroups as well. Next, when you work on a project iteratively, similar to your code base, the design of your system also needs to be version tagged, so we wanted to support that as well. So although this next one is not a hard requirement, we also wanted to explore if it's possible to let developers branch out from the original design of the system and work on some alternative versions if they wanted to. Next, the users also need to be able to go through previous revisions of the system and revert back to a previous version if they wanted to. Also, we needed to support atomic transactions so that if there was an error when you're handling a request, there won't be any corrupted data. Finally, because MyStekz is a multi-tenant platform, we wanted to do all these things in complete isolation from one tenant to the other. Okay, when I lay down these requirements, probably you might be thinking, well, Git should solve almost all these requirements, right? Well, that's what we also thought, but basically using a single Git client in your backend application has some problems. First of all, this is not scalable because if you had multiple instances of the backend running, you will have your data scattered across them. And secondly, if you had multiple asynchronous workers in a specific backend instance, you will have race conditions because all these workers will be trying to access the same data. Secondly, because any change you do is preserved immediately into the file system, it's going to be really difficult to implement atomic transactions with this approach. Let's say to solve the scalability issue, you decided to have a Git server, remote Git server that you can push changes to. So with this approach, still it's difficult to implement atomic transactions because you will still be keeping local checkouts of the repository in your Git client. And also it's going to be much slower as well because for a given set of operations, you now have to git pull, make changes, read write things into the file system and commit and then git push to the remote server. So because of this, we, as our first try, we decided that to develop this separate storage server, which exposes a Git interface via a REST API. So backend doesn't need to keep any local checkouts, which eliminates the issue with multiple asynchronous workers and multi-instance setup. We used this setup for a while, but there were multiple problems with this approach. First of all, the REST interface had quite a bit of an overhead, so that because if there's a lot of traffic between the backend and the storage server, that overhead became a really big issue for us. Second, in our implementation, storage server also kept local checkouts. So first of all, you had to deal with uncommitted changes if there was something wrong. And we could only support one branch, working with one branch at a time, because again you have a branch checked out. And also it's not scalable to have multiple asynchronous workers in this storage server as well, again because you have a checked out revision. And also still internally we are doing the same thing we could have done with the local Git client, and now we have this overhead of the REST API. This solution was very slow as well. So this is where we stumbled upon this awesome open source project called Gitly. Gitly is basically developed by GitLab for their own internal storage, repository storage. And it's a super awesome project, so we are really thankful for GitLab team for making this available for us. So Gitly actually, as I said, developed by GitLab as a replacement for their previous NFS-based storage. It provides horizontal and vertical scaling and eventual consistency. It provides fault tolerance out of the box as well. So overall, it's a really great project. Basically, if you had worked with GitLab CLI client locally, you actually have been directly communicating with their Gitly server. So what we loved about Gitly is it has a gRPC interface which provides us with the performance we need for the communication between layers. Gitly works on headless repos internally directly, which makes that Gitly doesn't have to keep a local checkout of any repositories. It's scalable out of the box, and also all requests are guaranteed by Gitly to be atomic. So let's take a look at few examples of how to use Gitly. So first of all, you have to establish a gRPC connection to the Gitly server. Then if you want to create a repository, for example, you invoke this create repository RPC, giving some information about the repository. Here comes the first problem with Gitly, because Gitly is only internally used by GitLab. It's not well documented. So it took me an embarrassingly long time to figure out that GL underscore repository argument is actually required. Although Gitly was not giving any errors if you didn't provide it, it just wouldn't work. But anyway, let's move on. When you want to get a file, it's a little bit more complicated. You can invoke this tree entry RPC, and you will get an iterator over the file data chunks. Stepping it up a little bit notch, this is how you commit something. You don't have to read through it. I'm not going to explain it either. But when you want to do a little bit more sophisticated stuff, like commit, get file tree, or move a file, etc., Gitly interface becomes much more complicated. So we decided that we need an abstraction layer over this. So that's where we decided to develop StekzVFS. Basically, StekzVFS provides an easier interface to work with Gitly gRPC interface and various errors that it throws. It provides a file system-like interface, so you can write very understandable code, at least in our application. And on top of that, it provides some various other functionalities, which I will go through in a couple of slides. So how do you establish a connection to Gitly via StekzVFS? You just don't have to do anything. You can just export this environment variable, and StekzVFS will take care of the connection for you. When you want to create a repository, we call it a file system in StekzVFS. You invoke this create function, and you will get a file system object. When you want to create a directory, you can access the root of the file system and call this create subdirectory function. And again, you will get a directory object, which you can then use to do various operations on it. But when you want to preserve the file creation, you have to call this commit function. It's the same thing as committing in Git. The commit function is available for you in the file system object or in a lower level in a directory level. You can provide a commit user and optionally some commit message to it. Creating a file is also as simple as calling this create file function. So you have to call this function in a directory object. One very tricky thing to do with Gitly is moving a subdirectory from one place to the other. Because Gitly works with headless repos, the concept of directories is very complicated. So when you want to move a directory, you have to get the deep tree structure using git tree objects, then get all the files in that tree structure, and then correctly update each of their file path information. But with StekzVFS, you have this high-level directory object which you can just move from one place to the other using this simple function call. And then StekzVFS will take care of all the file path updates for you. Next up, on any entity, a file, directory, or a file system, you can call this get history function, optionally giving some filters like the author, start and end date, and some pagination information, and get a list of history entries for that specific entity. Branching is also very easy. You can create a new branch, giving a branch name, and then once you have checked out that branch, you can just do all the usual functions on that file system afterwards. Tags are also the same story, but as you know, in regular Git, when you check out a tag, you are in this detached head state. Just keep that in mind. I'll get back to that in a second. So to conclude, these are all the functions available for you in file system class. I'm gonna pause a little bit. Yeah. So this is a directory class, and the file class. So you might be thinking it's just an abstraction over the Gitly interface, but it's a complicated answer for this. First of all, it's not just an abstraction just for the sake of simplicity or to hide implementation details. It's made to give you a different interface for the same data in Git. Basically, a more easy to use interface in our application actually. And more importantly, it saves you from some nasty complications in Gitly interface, which is not that straightforward always. But there's more actually. We have some additional functionalities on top of StekzVFS that we desperately needed, which is not available in Gitly interface and also with regular Git for that matter. So one of them is transactions. To explain it, consider this scenario. If you have a request to the backend fails for whatever reason, and you want to revert all the changes that you did to the system. This is usually what DB transactions are for if you are using RDBMS. As an example here, Bob requests to update a file, and backend takes that request, makes the changes, and commits those files, and then at the end, backend tries to write some logs, and it fails. So now immediately what comes to our mind is we can just drop the commit or revert it back. But the problem is dropping a commit is actually dropping a commit is actually an active process. So if the backend crashes right before you can drop the commit, these changes are going to be permanent in your system. So because when the backend comes back up again live, there's no recollection of what has happened before. The next problem occurs when you have multiple asynchronous workers working on the same repository at the same time. In this case, in between Bob's commits, Sarah also makes some changes and she commits them. And now you can't just revert the commit back because there can be conflicts there. So what we need is a way to contain transactions. Basically, it needs to support these functionalities. It has to be isolated from the transaction has to be isolated from any other transactions that's going on parallelly, and also it has to be isolated from any other changes you are doing to the file system outside any transactions also. The transaction has to commit all or none of the changes atomically at the end. And also, unlike the commit dropping mechanism we talked about, transactions should be reverted automatically at the end also if it was not committed. Also, finally, it has to be foolproof. So if someone mess something up inside the transaction, there won't be any corrupted state or undesired behaviors to happen. So we basically implemented that. This is how it works. It's very intuitive how to use it. You can just enter transaction context, and you have to enter transaction context on a specific file system, as you see there. And then you can carry out any operations you want. And when you exit the transaction successfully, all the changes that you have done on that inside that transaction will be preserved in that file system. If you exit the context without an error, all the changes that you did will be discarded. Okay, so taking a little bit more complicated example here, you can also create nested transactions as well. Here, as you can see, the inner transaction fails, but you catch that error in the outer transaction. So outer transaction exits without any errors. So intuitively, this will discard all the changes that you did on the inner transaction and preserve all the changes that you did on the outer transaction. So hopefully you'd agree that these kind of transactions are really useful. And also it was very useful in a practical sense for our application as well, because we could implement a unit of work pattern using this approach. So basically when you enter a business transaction, you start a VFS transaction, and no matter how many commits you do inside, all the changes will be either preserved or reverted back at the end. So I'll also explain how this works internally. It took a lot of head scratching, but at the end, I think we have landed on a very, very simple and elegant solution. So this is how it works. When you enter a transaction context, we create a separate branch based on the branch you are currently in. And any operations you do inside the transaction are done on the transaction branch and not the original branch. And when you exit the transaction successfully, we just merge the transaction branch back to the original branch. And if you exit the transaction unsuccessfully, you just don't have to do anything because we have not touched the original branch yet. Well, nothing. Basically, we just clean up that dangling transaction branch, but that's actually not mandatory. For nested transactions, the logic is exactly the same. We create another transaction branch now based off the parent transaction branch. And once you exit the nested transaction branch, we merge that nested branch back to the original parent transaction branch. So the beauty of this approach is, even if the backend crashes right when you are inside a transaction, you won't have any corrupted state because the original branch was never touched. So for unsuccessful scenarios, basically you don't have to just do anything, because so even when the backend crashes, you don't have anything to do there, only when the transaction was successful. Another very cool thing about this is when your backend crashes and when the backend comes back on, that transaction branch will still be there. So it's possible for you to resurrect that transaction if you wanted to. But we are not, taking advantage of that feature in our application. The next value addition we have on StekzVFS is permissions. Taking an example again here, this is the signature of file classes rename method. As you can see, there are two decorators for it. One is detached head guard, and the other is about read-write permissions. This is basically what a detached state guard is. When you check out a random revision or a tag and not a branch head, you will be in this detached head state. And you can read data in the file system in this state, but until you move to a branch head, you are not allowed to do any changes to the file system. For example, here we have checked out a commit tag, and now if you try to rename this file, you will get a detached head error. The second permission guard is read-write permissions. By default, when you get a file system object, you will be in a read permission state. In this state, you are not allowed to do any changes to the file system. So if you try to do something like this here, you will get a permission error. If you want to get a file system to make changes to, you have to explicitly state that. So this allows us to write very expressive code and also do things like passing around a file system object which is only meant to be read and not modified. So this brings us to the end of my presentation, but I want to lay down a few things that's not available in StekzVFS yet, but I would really like to see it there. First thing is conflict resolution. Right now, when two people parallelly start transactions, there's no way to let the user to resolve conflicts at the end if there are any. So the last person to finish the transaction will fail actually if there are conflicts. This is not a problem yet because MyStekz actually doesn't support collaborative working yet, but this is something we have to fix. or let multiple users work on the same transaction if you want to let them do real-time collaborations, for example. Second, StekzVFS already do cache in data if you read them, if you read the same thing over and over again. But we can't use that functionality yet in MyStekz Platform because if you have multiple instances of the same file system used by multiple asynchronous workers, you have to make sure that the caches are up to date on all of those instances, which is not implemented yet. So this is something also we need to work on. Third, although it looks pretty cool, transactions are not that fast because it requires you to create a branch and then merge it back on. Creating a branch is extremely fast, but merging is slow, relatively slow. So we have to find a better way to do transactions. Finally, we are only using one instance of Gitly in our production system currently. We should take advantage of the scalability of Gitly as well, which is already there. So that was the story of StekzVFS. Hope you guys like it, and thank you very much.